Hi, welcome to this talk on the patterns and practices for building resilient serverless applications. But first, let me define what I mean when I say resilience. The dictionary definition is the capability to recover quickly from difficulties or toughness. In other words, it's not about preventing failures, but to recover from them quickly. And as Werner famously said, everything fails all the time. It's a fact of life and there's nothing we can actually do about that. But what we can do is to build applications that can withstand different forms of failures and quickly recover from them. For example, in a data center, hardware fails all the time. And to withstand hardware failure, we run our application on multiple servers so we can withstand failures to individual servers. And since data centers, or in AWS terms, availability zones can go down in exceptional circumstances, of course, we run our application across multiple availability zones or even multiple regions to withstand failures that affect entire availability zones or regions. And since individual servers have a limited set of resources in terms of CPU, memory, and the bandwidth, the more user requests that you have to handle concurrently, the more resources that we are going to use. And a common failure mode is when there are too many requests and we saturate the CPU, after which latency starts to spiral out of control. Another reason why we need to scale out our application across multiple servers. And when we have a distributed environment where services often have to coordinate with and depend on other services, and one service experiences failures, and they can often cascade throughout the whole system and affect even those user-facing services, which of course is not going to make your customers happy because they have to experience interruptions when they try to use your app. And when you have a microservices environment with lots of microservices, it's quite a common problem that many of us have to deal with. So my name is Retry. I'm an AWS Serverless hero and a long-time AWS user. I have been running production workload on AWS for more than 10 years by now. And the last couple of years, I have focused on serverless technologies, including migrating a social network to run pretty much entirely on serverless a few years ago, which you can read all about on this link. Nowadays, I spend half of my time working with Lumigo as a developer advocate, and Lumigo is a troubleshooting platform for serverless applications, giving you one place to see all of your distributed tracing, all of your logs, as well as the state of your Lambda function during an invocation. The other half of my time, I work as an independent consultant, and I help companies all around the world go faster for less by adopting serverless technologies. So back to building resilient serverless applications. This diagram from Uri Fredrickson highlights 4 broad areas that we should consider when we think about resilience. And it's worth considering that Lambda gives us a lot of resilience out of the box, not least because we have an isolated execution environment for each and every single invocation. So if one user request uses up too much CPU or memory, it has literally no effect on any other user requests. And when you build APIs with API Gateway and Lambda, you get multi-AZ out of the box, as both API Gateway and Lambda deploys your resources to 3 availability zones by default. And both API Gateway and Lambda charges based on usage, so you only pay when users actually use your system. And what's more, you also get load balancing out of the box as well. When a HTTP request comes into API Gateway, it's routed to one of the available AZs, and again, you don't have to configure and pay for load balancers yourself. Finally, if you're using DynamDB as well, which by the way is also multi-AZ by default, you can also configure DynamDB tables as global tables and turn your whole API into a multi-region active-active setup, which is basically the gold standard for building resilient applications in AWS, but more on that later. So suffice to say that we get a lot of resilience out of the box with serverless technologies like API Gateway, Lambda, and DynamDB. But we also have to be wary of the built-in throttling at each of these services, especially as they don't always line up perfectly. And this also applies to timeouts as well, where API Gateway has the max integration timeout of 29 seconds, which is the hard limit, even though Lambda function itself can run for 15 minutes. And the same goes to when you process SQS messages with Lambda, where you have to consider the visibility timeout on the queue and how it relates to the Lambda timeout. The general recommendation is that the SQS visibility timeout should be 6 times the Lambda function timeout. And a common pattern for making your APIs more resilient, at least in cases where we need to perform CPU-intensive tasks, is to offload them to a queue first, so the API function can respond quickly to the caller, and we can perform those long-running CPU-intensive tasks in another Lambda function where we don't have to worry about API gateway's 29 seconds timeout. So this allows us to better absorb any downstream problems. For example, if we need to call a third-party API and if the API's latency is going up, we don't have to run the risk of getting timed out by API gateway after 29 seconds. And we get retries through SQS and then the delta queue support as well for poison messages. But a common problem here, at least with DLQ, is that we need some way to replay those DLQ events, especially if the original failures were down to temporary issues with the third-party services. And to do that, you can use the Lumigo CLI, which has got a bunch of useful commands, such as the replay SQS DLQ command that lets you replay messages from a SQS DLQ. So this pattern is great for find and forget task where the caller doesn't do anything with the response. So it just needs an acknowledgement that a task has been received and processed. But what if the client actually needs to have a response from us? So a pattern is called decouple invocation, where the main difference to what we were doing earlier is that we will return a location header in the initial response, so the caller can poll for the result until it's ready. And in this case, a request will come in, and our API function will queue up the task in SQS and then save a token in the DB table where result is null, as in not ready yet. It will return a 202 response with a location header, and in the meantime, the SQS function is going to pick up the task and start working on it. And when the client polls for the result and it's not ready yet, we will just return 202 saying, sorry, it's not ready yet, and here's the location header for when it would be available. And when the background worker finishes the task, it's going to save the result into DB so that the next time the client asks for it, we can finally return a 200 with the result. So it's pretty straightforward, but wait. Notice that we have a distributed transaction here, where the API function has to write to both SQS and DB in the same invocation, which means if we are to do this the right way, then we will need to make sure that if one fails, we then have to roll back the other. So how do we go about implementing distributed transactions properly? Well, that's the Saga pattern, which is the pattern for managing failures in a transaction where each action has a compensating action for rollback. And here's a talk from Katie McCaffrey if you want to learn more about the Saga pattern. And imagine you're implementing a transaction for a holiday app where you need to book a hotel, then a flight, then some car rental. Each of these actions, as well as the rollback, can be modeled as Lambda functions, and then we can use step functions to coordinate our Saga, so that given an input like this, where I'm visiting Dublin from London, the happy path is going to have me book the hotel, then the flight, then the rental, and then complete the transaction. But if there was a failures, then we perform the rollback action to undo any state changes that's been done so far. And if we have booked the hotel but couldn't book the flight, then we have to roll back both the flight as well as the hotel booking in reverse order. The Saga pattern is a very powerful and very useful pattern, but it's just extra stuff that we have to do. In many cases, we can actually architect the distributed transaction out of our application by using DB streams instead, where a Lambda function would then take those DB inserts and then publish them as tasks to SQS, so no distributed transactions needed here. Or better still, we can just do the work in the DB function. DB streams is already some kind of a queue, so unless we're getting something extra with SQS, we don't have to use it. And with DB and the Kinesis streams, there's also this interesting error handling behavior where messages are retried until success. which is very useful in situations where the only thing that's likely to go wrong is when some third-party service is having an outage. Then, since messages are retried until success, there's nothing for us to do. When the third-party system is back, we'll just continue from where we left off before the outage, which is awesome. The thing to keep in mind here is that DynamoDB streams only keep data for 24 hours, and there's no way to extend that. So if it's possible for outages to last for more than 24 hours, then we need to have alerting in place so that we can deal with any issues quickly before any data loss. Or we can turn on the on failure at destination, which is a new feature that was introduced at the reInvent 2019. Essentially, this is the DL queue or delta queue for stream processing functions. Another thing to keep in mind here is that the retry and success behavior also renders us vulnerable to poison messages. Luckily, nowadays we can also configure the max number of retries and also have the option to split a batch when in error so that we can quickly home in onto the poison message. As example, if the batch had 6 records, after the first attempt, it will be split into in half, and so that the second attempt will only have the first 3 records, then just 1 record, and from here only that 1 record will be retried up to the max number of retry attempts, which only counts the number of attempts for the same batch. So in our example, you start counting when we're down to that 1 poison message in the batch. So in total, that poison message can be retried a few more times than the max attempt value that you configure. You should use these 2 options together to avoid otherwise normal messages being discarded because of a single poison message in a batch. And when the poison message is eventually discarded, it's going to end up in your DLQ if you have configured one that is, and you should. The DLQ message is going to look something like this. The key thing to note here is that you don't get the message body, and you have to use the shard ID and sequence number to get it from the stream. And don't forget, you got to do this before the data expires from the stream. So again, you need alerting in place so that you can do this proactively or have some other process to automatically read the data from the stream. And as for using SQS with Lambda, since SQS is a polling-based service, there's actually a cluster of pollers that Amazon is operating on your behalf, polling from the queue and forwarding batches of messages to our function. And when our function finishes with no error, the poller calls SQS to delete the messages. Now the problem comes when our functions error, and so the poller doesn't tell SQS to delete the messages, even though some of them might have been processed successfully. So this message is going to get retried after the visibility timeout, and then after the max number of retries, hopefully only the poison messages is going to continue to fail and they will be delivered to the DLQ. Again, you should always configure a DLQ when you're using SQS. But the fact that the batch fails as a unit means that we have to deal with these partial failures. So I've talked about this along with a few other SQS failures modes in this particular blog post. Ultimately, I think you have 3 main options here. One is to use a batch size of 1, which would basically eliminate the problem altogether, but it can also hurt your throughput and add to your cost, since you need to have more Lambda invocations and more API requests to SQS to process the same number of messages in total. Or you can make sure that the processing logic itself is idempotent, which I think you should always aim for anyway, but it's often difficult to actually achieve, especially when you need to update the state of multiple systems, which would basically necessitate more complex machineries such as the Saga pattern. Which is why my personal preference is to put a try catch around every single message, and when all is done, check which message failed, and if there are no partial failures, then we just return success and let the poller call delete messages for us. Otherwise, we will call delete message ourselves, but only for the successful messages to manually delete them so they don't get retried. And then we're going to throw an error, which would leave the failed messages on the queue because the Lambda function is going to error and the poller is not going to call delete messages on our behalf. And then moving on to another common problem in microservices where sometimes doing the right thing can have the opposite effect. So imagine we have Lambda functions that need to call this service A, and at any moment in time, we have a number of concurrent executions all calling this service. And now imagine this service is having problems. Some of those requests are going to fail or time out, and to make our application more resilient to temporary issues, we probably have some retry and exponential backoff built into the application. And in normal situations, this is absolutely the right thing to do. And the AWS SDK does this by default as well. Except in this case, where service A is already struggling, it has to deal with the retries as well as a fresh request from new concurrent executions. And since it's struggling, it can't handle them all, so the failed request gets retried, and so on until the service is just dead on its feet. And this, my friends, is what we call a retry storm, where problems can sometimes be exasperated by doing the right thing and retrying failed requests. And the solution here is to use the circuit breaker pattern, where you will still have retries, but after a certain number of consecutive errors or timeouts, you will trip the circuit, and that's so that no more requests can be made to the service, and the ending request will just fail outright. We're just going to throw a circuit is open exception and not make a request to the service, which is struggling, and to give it a chance to actually recover. And instead, what we're going to do is we're going to let one request through every couple of minutes. And if it's successful, then we will assume that things are back to normal and we can close the circuit. Otherwise, we'll keep the circuit open and let another request through after another couple of minutes. So this is a really common practice in the microservices. The big question for a serverless application is, well, where do you put the state of the circuit, since concurrent executions, they don't share state? We can let every single concurrent execution just track its own state for its circuit breaker, which is simple and have no external dependencies, but it does allow more requests through, especially when you have new concurrent executions. They don't know the current state, so they have to figure out what the current state of the circuit should be. Or we can store the state in, say, a DB table that all the different concurrent executions can access, especially when they first spin up. Personally, I will start with the in-memory approach and upgrade to using DB tables if and only if that's not good enough, and you need to reduce the number of requests that gets through during an outage before you figure out that, hey, the service is having troubles, we should trip the circuit. And then there's the gold standard for building resilient serverless applications, which is to make them multi-region active. Imagine you have a REST API with API Gateway, Lambda, and DB all running in US East 1, and all sitting behind a Route 53 with a user-friendly domain name. Now, this setup is pretty resilient, as all the components have redundancy built in with a multi-AZ, but you are still vulnerable to region-wide failures. So to get to the next level of resilience, let's go multi-region. By deploying our application to 3 separate regions and to serve requests from all 3 regions all the time in an active setup, using Route 53 to route traffic to different regions, probably using geolocation or some latency-based routing. And to make sure that all the data updates are synchronized globally, we can connect the regional DB tables together as a global table and let AWS manage and synchronize the data for us. And finally, we're going to set up Route 53 health checks so that if one of the regions goes down for whatever reason, then traffic can be diverted to the remaining regions automatically, of course, subject to the TTL that you have configured on the DNS record set. This approach is not limited to APIs either. If you have data processing pipelines, for example, suppose you have a pipeline that ingests data from some upstream SNS topics through SQS and Lambda, and is written to a DB table, which is then used to power your own API with API Gateway and Lambda. And now, suppose your upstream system is already running in a multi-region active setup, then you can subscribe your queue to both the SNS topic in both regions and ingest data from both, so that in the event that one of the regions goes down for the upstream system, the pipeline will continue to work without you having to do any manual intervention. Amazon engineers call this static availability, where the system will continue to operate in the face of availability zone or regional outages. However, in this setup, you end up ingesting the same data twice. So you do need to perform deduplication somewhere. It can be done using conditional writes when you insert the ingested data into DynamoDB. And to make our data pipeline and API multi-region active, we will deploy the same setup to 2 or more regions and set up global table for all the regional DynamoDB tables. And then each region will just subscribe its SQS to both upstream SNS topics. So that once again, if one of the upstream regions goes down, the system continues to operate without manual intervention. Remember, static availability. And of course, we'll use Route 53 in front of our API gateway so that in the unfortunate event that a whole region goes down, then our system will just continue to operate. And you would self-heal once the TTL on the DNS record expires and API traffic is diverted to the healthy region, all without us doing anything. One of the great things about doing this with the serverless components is that there's very little overhead for having the extra redundancy compared to running containers or VMs, where the diluted traffic to each region and AZ means that we end up spending a lot of money for unused resources. The downside of having a multi-region setup is that they are more complex, everything from the deployment to monitoring, and they are also harder to test as well. And the best way we have for testing these complex systems is chaos engineering, which I'm sure many of you have heard about from the likes of Netflix or Amazon, talking about how they queue their servers in production at random to simulate infrastructure failures that results in the loss of EC2 servers, and see if the system can actually stay up when these infrastructure problems happen. It's certainly one way that you can apply the principles of chaos engineering in practice, but chaos engineering itself is much broader. And in the words of principles of chaos.org, chaos engineering is a discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And it has become increasingly important to many organizations because we are just building more complex systems now, which have more complex and hard to predict failure modes. And the thing about failure is that you can't choose when they happen. They're just going to happen and the moment is going to choose you. You can only choose how prepared you want to be when they do happen. So Gunnar, who is also another serverless hero, published a very helpful library that allows me to inject failures into a Lambda function so that I can use it to test, to see, say, what will happen to my application if DynamoDB's latency or error rate is up, or what will happen if a service that I depend on has an elevated latency. I can tease out these failure modes proactively and identify weaknesses in my system before they actually happen in production, and they will eventually because everything fails all the time. But what we can do is to build applications that can withstand these failures and recover from them quickly. And that's everything I've got, guys. If you want to learn more about Lambda best practices, please check out my new video course, Learn You Some Lambda Best Practice for Great Good at lambdabestpractice.com. And as I mentioned earlier, I'm an independent consultant. So if you want to see how we might work together, please go to theburningmonk.com to see what services I offer. So with that, thank you guys very much and stay safe. I'll chat to you guys online.